law of large number is something actually very intuitive. Consider a memoryless source. Here I don't need the source to be discrete. So, but the source supposed to take the numerical value. And so for each element, let's say x1 to xn, and consider the empirical average like yn as x1 sum up to xn over n. You write it better. What the law of large number claims is that like the empirical average basically will converge to the actual average. So in the sense that yn will just converge to expectation of x as n goes to infinity. So here, remember that for this, when we say a memoryless source here, each element x1 up to xn is basically ID variables. They are ID, random variables. And so therefore like the expectation of x1 is equal to expectation of x2 and so on is equal to expectation of xn. Here I just use so this expectation of x is basically equal to expectation of x1 and say x2 and so on. It's very easy to show the law of large number. Here, it's not here what I'm going to show is not a rigorous proof, but just trying to give some intuition. So let's compute the mean of this empirical average here. So for the expectation of yn is basically just expectation. Remember that expectation is a linear operation, therefore it is equal to expectation of x1 plus expectation of x2 and so on up to expectation of xn over n. And of course like all these are just equal to expectation of x, and so therefore like I'll just equal to expectation of x here. So the mean of the empirical average is equal to the mean of the source, and the variance of yn is equal to the variance, because these are all independent, will be just equal to the variance of x1 plus up to variance of xn. Let's write it this way. But variance of x1 over n is equal to 1 over n squared variance of x1. And so I have this variance of xn here. And again, like the statistics of all these x1 up to xn is the same, so I will just write this as variance of x instead. And so I have n of this, so I have n variance of x over n squared, so I have variance of x over n. So basically, the average the mean of the empirical average will converge to the actual mean, and the variance will converge to the variance of x over n. So as n goes to infinity, so this variance will just goes to 0. So therefore, apparently, yn will just converge to the mean of yn, that's basically expectation of x. So actually, this is something very, I would say, intuitive, but at the same time, it's very useful. Now let's consider our previous example. Let's say we have a discrete memoryless source here, n is basically the output of this discrete memory source x1 up to xn, basically outcome from flipping a coin, a bias coin. In our last example, we say like pH is equal to 0.2 and p tail is equal to 0.8, and n is equal to 10, let's say. Actually, let's not fix the n for the moment. And again, like what we're interested in is to see like what sequence each time. Okay, this combination we call a sequence. Again, what sequence is typical? And let's look at this expression here. Let's look at what is log p of x, where x is a sequence, a random sequence drawn from this discrete memoryless source. That is, x is equal to x1 blah 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 up to xn. So note that x here is a random variable, actually a vector random variable, and we're interested to look at what is this value here. But what is this value here is actually equal to, because this is a memoryless source, p vector x is just equal to px1 multiplied by px2 and so on up to pxn. And if I take a log of that, I will have sum over log px I, right? I is from 1 to n over n. So now what we have here is this log px is like we can construct another memoryless source that is output what? Output this log px here. And by law of large number, what we have is this empirical average of this source. So what I want to say is this memoryless source is output p log px each time. So I have a log px1 and then a log px2 and so on up to log pxn. And as we've shown here, the empirical average of the outputs here should converge to the actual average. So in other words, this empirical average should converge to expectation log px. This is by law of large number. But this expression actually looks very much familiar. I'm not sure you remember this. It looks familiar because the channel entropy is actually equal to the minus of this expression, is equal to expectation minus log px. So therefore this is just equal to minus hx. So therefore what we have here is px will actually converge to 2 to the minus nhx as n goes to infinity by law of large number.